Hello, this is the next video in a playlist that I'm calling General Linear Models, Design of Experiments. And I'm currently doing a little mini series on one-way fixed effects ANOVAs. And this is dealing with residuals. And I called it part 11 of 10. I wasn't originally going to cover residuals, but I am. And this is really an R illustration of the residuals, illustrating part 11 of 10. Now, in this series, I'm assuming that you have watched the first 9 videos, and we're covering an example out of a book by Montgomery called Design and Analysis of Experiments. It's the 3rd edition, and we're looking at example 3-1, tensile strength experiment. And it has to do with looking at the tensile strength of fabric. Tensile strength means how much force does it take to tear the fabric. And the fabric is made with a 15% cotton blend, a 20% cotton blend, 25, 30, and 35% cotton blend. And that's the example that we've been using throughout this. So I need to load all the data into a data frame called TSE, stands for Tensile Strength Experiment. So I have access to that when we cover part 11 of 10. So it's going to go through and actually rerun everything that we've done in the first 10 parts. So now here we are at part 11, and just to re-illustrate what we're doing is we run an ANOVA model on tensile strength by treatment, and we store it in the variable OWFE, which stands for one-way fixed effects. And if we look at the summary of this, the p-value is really small, it's highly significant, and that says there is a treatment difference between the different fabrics. So the tensile strength varies between these different types of fabric. And the residual, we fit a model of the data, and we hope that the model we create fits the data exactly, but it never does, but it's always close, and we want to see how close it is, so we look at the residuals. Now, in our model assumption, we assume that the error is normally distributed, has a mean of 0. And to do hypothesis tests and confidence intervals, we have to assume it's normally distributed, mean 0, constant variance sigma squared, and they're independent of one another. In part 11, we showed that the observed residuals asymptotically follow these results. So we want to see if this also holds. So if you just plot OWFE, which is, we stored the model in that variable, and I create a little 2x2 matrix to plot it in, we get the following. It's the residuals versus the fitted values. In this plot, we want the residuals to have roughly a mean of 0, and they do. The red line is pretty close to 0. And we want them to fluctuate around this line in a constant manner. And they do. I always jokingly say, squint your eyes, drink a beer. They look constantly, they fluctuate constantly around that line. Now, the normal QQ plot it's a way to assess to see if they're normal. And so all these dots should follow a straight line if they are normal. And we don't really have a big sample size, and so they, again, squint your eyes, drink a beer, they approximately follow that line. Now, I have a video out called Using R, QQ Plots versus Rankit Plots. And in that video, we describe in a lot of detail what a QQ plot is and what a Rankit plot is. And they all want to assess the normality of the data. Now, this scale location, it takes the absolute value of the residual and then takes the square root of it, or and we want this line to be roughly flat, and it sort of is, and we also want it to vary along, constantly about this line. Now, there's pluses and minuses with each of these plots, but these are the standard plots that R produces. And here in this bottom right, it produces the standardized residuals by each treatment combination, or in this case, there's only 5 different treatments. And again, we want the residuals to be centered around 0, and then again to fluctuate around it in a constant manner. And in these, there's really nothing alarming that would say the model doesn't follow, a one-way fixed effects de novo. We could produce this top left graph by just plotting the fitted values by the residuals, and then that would produce the same plot. And of course, you could give it fancy labels and a title. A histogram would show, we would want this to be normally distributed, and again, since there's so few observations, it's hard to say whether this does or doesn't follow a normal distribution. We could create the QQ plot and fit the line. And here, they sort of don't follow that line in the same way here. But with so few observations, again, there's nothing that just, gets me too excited to say it deviates from our assumptions. I like a strip plot because it plots the data in tensile strength by the group. And here, the constant variance, these should all be spread apart about the same distance. And if you see, they roughly are. And there's some tests. There's 2 tests that we can run and to see if there is a homogeneous variance. Is there constant variance? In this first test, the null hypothesis is that there is homogeneity of the variances, and the alternative is that there is a non-constant variance or heterogeneity in the variances. And so since we don't reject the null hypothesis, then we assume that there is a constant variance associated with this. Bartlett's test is also a similar type test. And again, the p-value is small, so we don't reject the null. So there's, no evidence to say that there isn't homogeneity in the variance, meaning there's a constant variance. And we can just plot the data. But this, since treatment is a factor, it creates box plots. And again, since there's not much data, some of these box plots don't look very, box and whisker like. But again, this is the data, and they sort of have a constant variance fluctuating about it. All right, well, that's all I have for this video. Hopefully you enjoyed that. I sure did. Please like the video and subscribe so you don't miss the next one. Thanks. Bye.